If the goal in our application is to provide consistency, then a technique that we can use to do that is something called sharding. And sharding is a technique that provides strong consistency. We're not talking about eventual consistency. This is for strong consistency. Now, I will mention that when we talk about sharding, we're not talking about at the database level. A lot of databases support a technique called sharding or consistency. The technique is basically the same. However, this is done at the application level rather than at the database level. Now, the advantage to doing it at the application level is, first, it means that we're not limited by the features of our database. We may have chosen a database that provides us with high availability, for example, instead of strong consistency. This allows us to bring strong consistency into that application, even though the database doesn't necessarily support it. So that's one of the advantages. The other advantage is there are techniques we can use here that minimize the amount of communication that we have to do between the application and the database, and we'll talk about what those are. But what that means is that it means that you have less communication with your database, which means your database is less of a bottleneck, and it can also provide you with some nice performance boosts as well. So what is sharding? So sharding partitions entities or actors in the domain according to their ID. So we have some unique identifier within our application, and we partition according to that. So in our example here, we see that we're dealing with the reservations system in our barbecue restaurant. And so we have our reservations are labeled with something like A, B, C, D, E, F. What we have done is we have taken reservation A and B and we have grouped them into a shard. So groups of entities are called a shard. Now, each entity exists in only one shard. So looking at the diagram again, you'll see that reservation A exists in the shard AB, but it doesn't exist anywhere else. It only exists on that shard. Each shard exists in only one location. So again, looking at the diagram, the shard AB exists on node 192.168.1.1. It doesn't exist anywhere else in our cluster. Now, this means that each entity lives in only one location. You can only find reservation A in shard AB on node 192.168.1.1. You won't find it anywhere else. Because each entity lives in only one location, we've eliminated the distributed system problem. Remember, when we have a distributed system where we have two pieces of the system that are the expert in some piece of data, or that we are trying to get an opinion about some piece of data from, then we have a distributed system problem. We have a problem trying to synchronize the information between those two pieces of the system. In this case, we say that if you want information for reservation A, the expert for that information only exists in one place. It's only in one place in the cluster. And as a result, we don't have a distributed system anymore. Reservation A is only in one place. It's not distributed in any way. This means that it can act as a consistency boundary. This is sort of like having a lock, for example. When we have a lock, we eliminate the distributed system problem by making the lock only exist in one place. In this case, instead of using a lock, we have the entity that handles the messages for that particular piece of data only exist in one place. It's the same basic concept, it's just a slightly different implementation. Now, in order for this to work, we need to know where all of these entities live. To do that, we have a coordinator. The coordinator ensures that traffic for a particular entity is routed to the correct location. So if we have a message like cancel reservation and it is identified for reservation ID C, then we can see where reservation ID C lives and we can direct that message as appropriate. Meanwhile, if a move reservation comes in for reservation ID B, we can direct that one to a different location. Basically, we take the ID and we use it to calculate the appropriate shard. There's usually sort of an algorithm that does this. Based on the ID, we compute the shard that we need to go to. All traffic for a particular ID goes through the same entity. So any messages that have reservation ID B all go through the same entity. This is again what allows it to act as a consistency boundary. Because it is going to see all of the messages, it can ensure that they are ordered appropriately. It can ensure that there's no conflicting information between them. It can do all of that work. Aggregate roots are a good candidate for sharding. So when you're trying to determine where to put your sharding, start with your aggregate roots. You may not stop there. You may decide later on that there's a piece of your aggregate root that would also benefit from sharding, but start with your aggregate roots. That's usually the starting point. Now, a very important thing here is it's critical that we choose an appropriate shard key and an appropriate algorithm for computing the shard key. If we choose that poorly, then what we get is unbalanced shards. And so we can see in our example here, we've chosen the first name of the person that the reservation is for. Now, depending on what part of the world you live in, there are certain names that you will see are fairly common. In my part of the world, at least, names that start with A are pretty common. So I gave some examples here: Amy, Adam, Ada, Alan. There's a lot more that we could go into, but this is a very simple example. On the other hand, names that start with the first letter Q, there's a few, but there's not a lot of them. Now, what we've done is by choosing the first name as our shard key, it means that we end up with unbalanced shards. The shard that contains the letter Q is going to have a small number of entities, whereas the shard that contains the letter A is going to have a large number of entities. As a result, it will be unbalanced and our load will not be well distributed. So a good shard key provides an even randomized distribution. So a common strategy for shard keys includes using a UUID. UUIDs are fairly random, so they work fairly well. The other thing you could do if you wanted to use something like the first name is you could take a hash code of the first name, which takes our not very random names and turns them into something that is fairly random and fairly well distributed. So you could use a hash code here. That's an effective technique as well. There are other techniques. You can specifically generate a shard key for particular records. There's other techniques as well. But the key is that we want a randomized, even distribution. Dates typically are a terrible approach to this. If you take a date or a timestamp and you use that, the problem is that often what that will do is new data will typically end up on one shard and old data will end up on another shard. New data tends to be more active in most systems, which means that you'll, again, have certain shards that are very active and certain shards that aren't doing much. On the other hand, if you take that date and you reverse it, so you turn it into a string and then you reverse the string, that might actually be an effective way to do it. It depends on how that balances out. So there are ways that you can take things like this and turn them into effective shard keys. So remember, poor key selection results in hotspots. Another key aspect here is that you should aim for about 10 times as many shards as you have nodes. So you don't want one shard per node, you want about 10 shards per node. The reason that we want that is because if you think about it, if you had a cluster of, say, 3 nodes and each node had only one shard on it, then if one of the nodes went down and you had to rebalance those shards among the remaining 2, what you would end up with is one node that hosts 2 shards and one node that hosts 1 shard. So you have, again, a hotspot where one node is doing twice as much work. On the other hand, if you wanted to scale up and you wanted to add a 4th or a 5th node, you could add the nodes, but you wouldn't have any shards to distribute amongst those nodes. So now you're, again, stuck in a situation where you have one node that's doing no work, and scaling up isn't going to help you. So if you go for about 10 times as many, that gives you some flexibility to scale up, and it also gives you some flexibility to scale down. And that's the advantage to doing that. Now, in the Lightbend ecosystem, Akka provides cluster sharding as a means to distribute actors across a cluster in a sharded setup. So if you want to do this in the Lightbend ecosystem, what you do is you create an Akka cluster. So this does require the Akka clustering features. And then you can use the Akka cluster sharding library, which will allow you to distribute your actors across a cluster. It's very, very easy to do. Most of the work is done for you behind the scenes. All you have to do is provide an appropriate sharding algorithm and a couple of other small things, and it will do all the rest of the work for you. So it's a very, very powerful tool. Logem persistent entities. leverage ACA cluster sharding to distribute the entities across a cluster. So if you're using logem, again, this is built in. If you use a persistent entity, you automatically get this, and there's no additional work required beyond the work to use a persistent entity. So that's built into logem as well. So both of these are built into the Lightbend ecosystem, and you can use them very trivially within your application.